This is a universal testing machine made by Tinius Olsen, about 1970 vintage. Universal testing machine means it can do a variety of tests. It can do compression testing, bend testing and tensile testing. They're mainly used for tensile testing, which is what we're going to do this evening. This is another universal testing machine, much older, from about 1940, an Avery machine. Again, it will do a series of tests. It will do compression testing, it will do bend testing, but as I said, it's also mostly used for tensile testing. This particular one, we use a lot of full section plate and full section bars on it. It's set up to do those sorts of samples. This is our second round of tensile testing. Tonight we're going to test more realistic samples, more real world, and we have some specimens prepared, two here. First one is a 1040 steel, which has been normalised, and the second one is an aluminium copper alloy with 3% copper, which is an age hardening alloy which has been heat treated. You'll notice that the samples have been machined. This section here represents the original gauge length, and it is a proportional test specimen. By that it means that the actual gauge length is 5 times the diameter. That is exactly the same as 5.65 square root of S0, which is the original area. So according to AS 1391, we use a proportional test piece where the gauge length is 5 times the original diameter. And there are some centre punch marks here. They are stamped at 50 millimetres, so the actual original diameter is 10 millimetres and the gauge length is 50 millimetres for both samples. So the aluminium one is stamped as well, and the steel is both stamped. They are important for us to work out our elongation once we have finished the test. First sample we've got in is a steel sample, and you can see it's held in the collets here. In between the sample there is an extensometer there, which is an electric extensometer, which actually powers a drum over the other side here, and the drum rotates as the extensometer extends, and with the applied load this needle moves up here, and as the needle moves up we get a reading of the load. So we're going to produce again a force extension curve. In this case we're only going to go to the point of yield. The yield or proof stress for a material is very significant for engineering and engineering design, so it's important that we do an accurate calculation for that, and that's what the graph's there for. See the needle coming back at the yield. Past the lower yield, back up again. Taking the sensometer off, we don't want to get damaged. So we've achieved maximum load. The sample should be starting to neck down now. You can see it necking in here. Getting ready to break. So as measures of ductility, we need to actually determine the final gauge length. It is 66 millimetres. So the original gauge length was 50 millimetres, the final gauge length is 66 millimetres. We also need to determine the final diameter where it's necked in. Reduced diameter is 6.1 millimetres. The maximum force the machine achieved was 44 kilonewtons. If you remember, the yield was at around, the lower yield was about 25.5 kilonewtons. This is the graph produced from the steel tensile test. The scales are magnified, so the extension scale is actually magnified, as is the force scale. Every 10 millimetres on the force scale is worth 2,500 newtons, and you can see there where the lower yield is, it works out to be 26.25 kilonewtons.